Okay, welcome back everyone. So in this mini lesson we're going to be talking about work and energy, and we'll start off with the conceptual definition, um, and then we'll talk about how to use it. So work and energy are really important, but the concept is kind of weird. It's kind of circular because what we could say about work is it's basically something that changes the energy of an object from one form to another. So when we talk about the different forms of energy, of course we're talking about kinetic or potential, and there's lots of different types of each of those. Um, and then when we talk about energy, energy is kind of defined as the ability to do work. And this is where it's weird because it seems like it's a circular argument that we, sort of define them in terms of each other. But it's a little bit easier if we sort of talk mathematically about what work actually is and how it relates to energy. So the math definition of work, well, the level of detail depends on your class, but basically we want to think about work as being equal to, you take your force vector and then you do a special operation called a dot product, and then you take your displacement vector. So this is force and this is displacement. And work is defined as the, quote, dot product of the two. But depending on your class, you may not learn about this so much. It's just as good to say that work is equal to the amount of force you have, the distance you move an object, and the cosine of the angle. And this is the angle between the force that you're applying and the displacement. So this is very useful, and a lot of people will use this equation when they explain work. And just as a little side note, another way that you can think about this is actually the amount of force parallel to the displacement times the displacement. So if that seems kind of weird, let me give you an example. Let's say I have a force which is going at some angle above the horizontal. Let's say it's, I don't know, 35 degrees. And let's say that I'm using this force to drag something, and so the object that I'm moving, maybe it's a box, is actually displaced horizontally. So what my definition tells me is that the work that I do is equal to the amount of force, which is parallel to the displacement, times the displacement itself. So let's get rid of the displacement for just a moment, and let's look at how much force is actually parallel to the displacement. So if the displacement is this way, then we can use what we know about sine, cosine, and triangle trig and kind of treat that force kind of like it's the hypotenuse of a triangle. And one leg of it is what we could call force parallel. And this is the amount of force that's parallel to the displacement. And if you remember your definition of sine and cosine, this is going to be equal to F cosine of theta. And so if we multiply those things together, f cosine of theta and d, that gets us back to our definition up here. So that's kind of the idea, and that's the really important thing to keep in mind. And so what this means for us is that we're going to have the most amount of work, the maximum amount of work is going to happen when the force and the displacement are parallel to each other. Okay, so in this case, the angle would be 0 degrees and the work would just be force times distance. And you can check out another video for an example of this, but this is without any numbers. You can also have a negative amount of work being done, and that's if you have a force going one way and a displacement going another. So this is where the angle is 180 degrees, and that gets you a negative sign because the cosine of 180 is -1. So you pop that into the equation and you get negative work done. You can also get 0 work done. Oh, and by the way, negative work often happens with things like friction. You can also have 0 work done, and I'll try to show you a demo of this in class, or perhaps your teacher will. And this happens when you have a force and a displacement at a right angle, and the cosine of 90 degrees is 0. So anytime you have force and displacement at a right angle to each other, you have 0 work being done. And a good example of this is in circular orbits. So with the Earth going around the Sun, it's not quite a circle, but it's pretty close, and at any point the force of gravity is going to be pulling inwards. So this is the Earth right here, and maybe there's the Sun. And at any time the displacement of the Earth for a really short time is going to be exactly 90 degrees. So one last thing about work is that oftentimes you study areas and slopes of graphs, and we've done that a lot in the past. And one thing to keep in mind is that if we have a force versus displacement graph, if I have a constant force, or if I have some sort of changing force, whatever the case may be, the area underneath the graph, so the area underneath the graph of force versus displacement is work. And that's because, again, we have to multiply force times displacement. One final note is units. Okay, so force, we always use newtons. Displacement, we always use meters. And that means that work is going to be newtons times meters, which is what we call joules. Okay, so that does it for this one. Be sure to take a look at some of the other videos on this topic. We'll work some example problems and go from there.